So from this triangle it's quite evident that this sine delta by 2, that is sine of this angle, this small angle, will be its perpendicular divided by its hypotenuse, where perpendicular is the half of this length, that is IR x by 2, that's IR x by 2, and hypotenuse is the voltage VR. And of course you'll see that IR is leading to this VR by an angle theta, which is equal to delta by 2. This is a leading angle. So here delta by 2, which is equal to theta, can be calculated as sine inverse of IR x by 2 divided by VR. So cos theta can be equal to, cos theta can be written as, that is the power factor angle, will be equal to cos of sine inverse of IR x by 2, which I have not written over here. Actually this was the explanation for question number 19 in objective, which I have given you for performance of transmission line. In that it was asked you that what will be the value of power factor if the voltage regulation will be 0 for a system having R is equal to 0, pure lossless system. That is this system, that is VR is equal to Vs for this type of a system. And what will be the condition of the power factor? So power factor will be this, and in that case voltage and this reactance was given in per unit. That means VR was given to be equal to 1.0 per unit, and when VR is equal to 1.0 per unit and we are calculating the voltage regulation at full load, IR is also equal to 1.0 per unit, because at full load current this IR is taken to be 1.0. When IR is equal to 1.0, VR is equal to 1.0, this theta, which is delta by 2, is equal to sine inverse of x by 2. This x has to be also in per unit. It is given as, this x is given as 0.6 per unit. This has to be in the per unit, in the per unit and on the same base. I will let you know what this is when we study the per unit system. For the time being, just remember it, what is its value. The per unit value of VR is 1, the per unit value of IR is 1, and per unit value of x is equal to 0.6. So finally it becomes cos inverse of cos of sine inverse of x by 2, where x is 0.6. It will be cos of sine inverse of 0.3, because 0.6 by 2 is 0.3. Again the power factor will be leading. It comes out to be 0.9 something, I don't remember. Now you can calculate it and you can match it with the option which is there. I hope you understood this. This was simple. Now coming back to other question, which is actually from the parameters of the transmission line. In this case we have a simple single phase transmission line whose power conductor is given by P1 and P2, which are 3 meters apart from each other, and they are placed below them are placed a telephone line of two conductors T1 and T2. They are placed 2 meters below, shown here, 2 meters below they are, and they are apart from each other 0.8 meter. They are symmetrically placed below. That means this line is actually a vertical line which shows the symmetry of these two. Actually this is the pole on which they are tied. And power line is having a current of 100 amperes, and assuming that the current flowing through this T1 and T2 is 0, we need to calculate the flux linkages due to these conductors in T1 and T2, that is telephone lines. And due to these flux linkages and the current flowing these two, we need to calculate the voltage in the telephone lines. What will be the voltage induced? So the first thing we will calculate the flux linkages of this conductor because of this conductor and this conductor. We know that the simple formula for this, I will represent it by lambda T1, where lambda is the flux linkage of conductor T1 due to this current and this current. It will be equal to 2 into 10 power minus 7 I, that's current flowing through this, ln of 1 by d1, that is the distance between these two, that is d1, minus, since current flowing this return conductor will be minus I, that's why here I have written minus I, ln of 1 by d2. you will see that this d2, since they are symmetrically placed, this will also be at a distance of d2. I have written here d2 Weber per meter. So it comes out to be, since I can take this current I outside, and by using the properties of logarithm, this can be ln of a minus ln of b will be equal to ln of a by b. It comes out to be ln of d2 by d1 Weber per meter. Similarly, flux linkages of conductor T2 will be equal to 2 into 10 to the power minus 7 I ln of 1 by d2 minus I ln of 1 by d1, where this I is current flowing from this through this conductor, and the distance is d2. That's why first it comes out to be d2. And from this uh, power conductor P2, current flowing minus I, and distance from here to here is same distance as here to here, that is the d1. That is minus I ln of 1 by d1. So the flux linkage of the second conductor will be similarly 2 into 10 to the power minus 7 ln of I ln of d1 by d2 Weber per meter. So flux linkage of the telephone circuit is, that will be the difference of the two, because one conductor will link this conductor, this flux can link in this way, and this flux can link in opposite way. So the total flux will be the difference of the two fluxes. So it will be equal to lambda t1 minus lambda t2, that is 2 into 10 to the power minus 7 I ln of d2 by d1 minus 2 into 10 to the power minus 7 I ln of d1 by d2. It comes out to be, by simplification, 4 into 10 to the power minus 7 ln of d2 by d1 Weber per meter. So MPT, that is mutual inductance between power conductor and telephone conductor, is lambda t by I. So we simply have to divide it by I. Here it is I. It comes out to be equal to 4 into 10 to the power minus 7 ln of d2 by d1 Henry per meter. So now the simple calculation, you just have to put the value of d2 and d1, you get the value of MPT. D1 is equal to 1.1 square plus 2 square, that is equal to 2.2825. D2 is equal to 1.9 square plus 2 square, that is 2.7586 meter, and MPT comes out to be 0.0758 millihenry per kilometer. Just please put this value in this equation, you get the value of this. Simply d1 and d2 you can calculate from here by symmetry. This value is 2, and from here to here you will see that from here to here it is 1.5, and from here to here it is 0.4. That means from here to here it will be 1.1. Similarly, you can calculate d2. Now voltage induced in the telephone circuit will be simply j omega L into I, where we can this inductance is represented by M, that is mutual inductance MPT. J omega, it is a 50 hertz circuit, that is 100 pi, 2 pi into 50, it is 100 pi into MPT into 100. It comes out to be 2.379 volt per kilometer. This question was perhaps from the transmission line parameters, question number 7. That is, I have given you in the assignment, the first assignment.